Hi there. Today we're going to talk about gas mixtures. So what's going to happen when we put a couple of gases together? Well, the nice thing is this is one of the most obvious and mind-numbingly easiest laws possible because all of the other factors are going to stay the same, and the result is going to be quite simple here. So what if we have a situation where we have here pressure 1, right? So if we have pressure 1, and you'll notice that it is at 1 atmospheres worth of pressure that's there, right? And we take a second gas over here, which we'll call pressure 2, and that guy is at 2 atmospheres there. So again, that guy there is at 2 atmospheres. What's going to happen when I take pressure 1, 1 atmosphere, and pressure 2, 2 atmospheres, and then combinify them into a brand new container that has all of the same conditions as the other containers had over here, right? So everything else is the same for our new container. The only difference is that everything is now smushed together. Well, it's not too much of a shock for us to figure that, assuming there is no chemical reaction between the two different substances, that the 1 atmosphere and the 2 atmosphere are added together to give us a total of 3 atmospheres there for our last guy. Or the simple fact is that the total pressure is equal to P1 plus P2. So this goes together, and it's called Dalton's law. And Dalton's law of partial pressures simply says that the mixture pressure, the total pressure, is equal to the sum of the individual pressures. So the total pressure is equal to the sum of the individual pressures. P1 plus P2 is equal to P total, or if there's 3 or 4 or 5 or 6 of them, add them all up and you get the total. Now, having said that, there are a couple of silly, sneaky little things that the AP folks are going to do to you. Please note that in our first one here, pressure 1 is being represented by 5 blue spheres here. Maybe those are atoms of whatever, right? Neon or argon or krypton or anything, right? And in pressure 2 over here, right, please note that they have given you more. Now, one of the things that they like to do is they like to not give you, for example, this value. They'll be sneaky about it. They won't tell you what that is, right? And so therefore they won't tell you what that is. But it doesn't matter, because if you know what the first one is, and assuming the conditions are stated that the second one is the same as the first one, remember that the ideal gas law says that it doesn't matter what the gas is. It doesn't matter if it's a big gas or a small gas. What matters is how many moles of it or how many particles of it are present. So remember, here in our first one, we had 1, 2, 3, 4, 5 representative spheres in our first container. And in our second container, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 representative spheres in a container of similar size under similar conditions of temperature and so forth. So because of the fact that there are twice the number of green particles as there are the blue particles, you can infer from that that this is going to be twice the pressure of our original pressure because of the number of particles that are there. And then when we combine them all together, now there are 15 particles in our new one here if you were to add them all up, which is why the 15 particles is going to give you a proportional 3 atmospheres of what's going on there. So sometimes they tell you, but they don't tell you in the problem. They tell you by giving you a picture that you have to infer what's going on from there. One of the things that, if you want a little bit more mathematical view of things, I could give you a more mathematical view of what is going on. So, for instance, in this container here, right, if I had not told you what that pressure was, but I had given you all of the rest of the information, you could tell that the pressure here is going to be equal to nRT over V. So the pressure of this guy is going to be 0.01 moles times R, and we'll go ahead and use the 6236 liter millimeter per mole Kelvin. times the temperature, which is 298 Kelvin, right? Divided by the volume, which is a 1 liter flask. So if I were to take all of that and do all the math on it, then the pressure for this guy would end up being about 186 millimeters of mercury, which is what it shows there, right? Now, please note that in our second container over here, which is also P is equal to nRT over V, right? The pressure is going to be equal to the same process, but please note that the only difference in our pink container over here versus our orange container is that our pink container has half the number of moles of oxygen, whereas this has twice the number of moles of nitrogen, but nowhere in this equation did we even take into account the fact that it was nitrogen, because it doesn't matter for the ideal gas law. And so consequently, the only thing that matters here is that this guy is 0.005 moles times R, which is 6236 liter millimeters of mercury per mole Kelvin, times the 298 Kelvin divided by the 1 liter. And again, when you do the math on all of this and multiply and divide everything out, you get that the pressure is 93 millimeters of mercury, which again is not surprising, because the only thing that's different is that this guy is half of this guy being 1. So the pink guy is half as much as the orange guy there. And then if we were to take both pink and orange and shove them together into, again, a similarly sized container, the only difference now is that this number here is going to be 0.015 moles total. And so consequently, you're going to end up with a 279, which is, again, not a big shock, because it's really just these two numbers added together. And that's going to get you the 279. So again, Dalton's law is pretty darn easy. It's simply saying that the total is equal to the sum of the individual pieces that are there. Now, you do have to be a little bit careful with how things are done. One of the things that they're going to ask you about here is air, I suppose. And please note that air is a mixture. So air in its totality is made up of mostly nitrogen, but some oxygen, and then less than 1 or 2% of all of the other substances that are there, depending on where you are on the planet. But that is a pretty good indication of what's going on. About 98% of everything that you breathe is nitrogen and oxygen, 77% of which is the nitrogen. So please note that the individual pressures of each of these guys add up to be the total pressure here of a normal atmospheric pressure of 760. It's just that each of these gases is exhibiting a different proportion of those gases. All right. We'll talk more about air being a mixture in one of the labs later on. You do have to be a little bit careful, though, because it's not quite as easy as that if they go and do one little wrinkle on you, which is to change the volume. So take a look at this problem. It says that we have krypton atoms at a pressure of 2 atmospheres and 1 liter of volume. So this guy here is 2 atmospheres and it's 1 liter. And then in container B, it says I've got neon over here, and the neon is also in a similar 1 liter container, but please note that it did not give you the pressure. But you don't have to have it, because this is 3 individual particles, and this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 4 times as much, and so because there are 4 times as many particles that are present, you can infer that this is 8 atmospheres worth of neon atoms that's there. Now what they're going to do is they're going to take this and they're going to shove both of these containers, but they're going to put it into a new container, and that new container is actually a 4 liter container. Well, there's a couple of different ways that you can go about doing this process. you can do each individual gas and add them up, or you can add them up and then do each individual, then change the total. Let's do each individual gas first. Let's take a look at what's going to happen with the krypton. The krypton is starting at 2 atmospheres and 1 liter, and it's going to be going up to 4 liters. So the volume is quadrupling. Well, we should know that from Boyle's law, if you quadruple the volume, then the pressure should decrease by a commensurate amount. And so, as far as the blue krypton is concerned, the pressure of the blue guys over here should be down to 0.5 atmospheres because the volume went up by a factor of 4, and so the pressure has to drop by a factor of 4. Same thing over here. If these red gases that are over here, if they started at 8 atmospheres and 1 liter, and we quadruple the volume, that means the volume has gone up by a factor of 4, so the pressure of the red that's over here has to go down by a factor of 4, so the pressure of red is now going to be 2 atmospheres in my new container here. So what then is the total amount for the red and the blue? Well, if the blue is 1/2 and the red is 2, then the total amount in my new container is going to be 2.5 atmospheres because I changed the blue and I changed the red, and then I added them up total in my new container. The other thing that you could have done, because each of these guys started at a liter, is you could have simply put these guys together and said, to start, we started with 10 atmospheres and 1 liter. And so if we started with 10 atmospheres and 1 liter and then went to 4 liters here, so the volume went up by a factor of 4, so the pressure has to go down by a factor of 4, which is why we end up with 2.5 atmosphere. 10 divided by 4 is 2.5. So just be careful if they go and they change the volume on you, or they change some other factor on you. You might have to take that into account when dealing with this, because it's perfectly reasonable for that to occur. So all of the other gas laws are still in effect, but the short of it is Dalton's law is one of the easiest laws ever. The total is simply equal to the sum.